Good morning. Good morning. I think this thing works. Can you hear in the back? I think it's working. Good. Welcome today. Before we get started, we are extremely fortunate today not have one but two wonderful musicians from the Cape Philharmonic, and let me introduce them to you if I may. We have Andrea Esau, who plays the oboe, and Beatrix Dutoit on the clarinet. They have a special surprise at the end, which I've asked them to do. Today is Woodwinds, but let me mention to you, you notice up front here there is a safe and a closet. And they're locked for reasons that everybody in this country understands. And getting a key to them is not easy. So yesterday there was a power problem, of power failure, and that's why everything went off. But getting someone to come and unlock that thing so that we could reset the power took most of the time. So I apologize for that. I'm sorry. Presumably, ESCOM is doing its proper thing today, and we won't have that problem. So today I want to come to an instrument that is fairly hard to understand, and I am resisting doing any algebra, so there are no serious formula discussions on the board. But there is a little bit of arithmetic, and there's some fairly hard physics. My hope is you get what you can. There's no exam at the end, and so it isn't required that you understand. But it is important, and it is the reason that these instruments, as we saw with Miss Van Renen's French horn on Monday, it's the reason for the bell. Without the bell, there would be no sound. So that really matters. And I want to talk about that. Anyway, woodwinds. These, as with brass instruments, what's vibrating in these cases is air. And of course, we can't see the air, but it all depends upon what one of the first people to investigate the properties of air back in the 17th century, 18th century, Robert Boyle, called the springiness of air. Now, there are molecules of air in this room, and it is hard to imagine both how small they are and how many they are. Take an ordinary room in your house, a simple bedroom, not a huge room like this, but a simple bedroom. It's got air molecules. If I could take those air molecules and if I could put them end to end, they would make a chain that would go around the Earth 25,000 million times. Okay? And my favorite example is here's a bottle of water. Okay, it has H2O molecules. If there's one thing that everyone seems to learn at school is that water is H2O, two hydrogens and one oxygen bonded together. And in this bottle, there are a lot of water molecules. In fact, there are more water molecules in this bottle than there are bottles of water in all of the oceans on Earth. Okay, so you go out and look at the Atlantic sometime and imagine how many times you can dip this bottle in the Atlantic, in the Pacific, in all the oceans on Earth. More in here. And I calculated that, so I guarantee it's correct. It's not, because most of what I tell you is stuff I read in books, but every once in a while I actually can check something. And so I did that. Now, air molecules are moving all the time. They're moving around and bumping into you everything. And they move randomly, and they move with incredible speeds. And at the room temperature and pressure, the average speed of an air molecule is 500 meters per second, which is about the speed of a bullet. And it's the banging and clanging, as Boyle said, of these molecules is that we call pressure. And it is the random motion of these molecules, the motional energy, that we call heat. So it is the collision of these molecules with the insides of your lung that keep the weight of the air from crushing your chest. And what really is amazing, it is the molecules banging on the wings, the top curved wing of an airplane and the bottom wing of an airplane, and making different pressure that allows these super jumbo A380s to lift off the ground with 550,000 kilos of takeoff mass, which is just amazing. And it's all due to these little tiny molecules that are banging into the sides. And so even though I know how it works, I still don't really always trust it. I also once taught at the University of Washington, where Seattle, in Seattle, and that's where Boeing was located. And a lot of the engineering students I had would then graduate and go to work for Boeing, and I really then worried about flying. However, they seem to make it work. Now, there's a lot of discussion about woodwind instruments. In particular, what I'm curious about is there has been discussion in the making of flutes about whether a gold flute or a silver flute sounds any better, and I have no idea the answer to the answer of that, or a wooden recorder versus a plastic recorder. And I brought my little recorder because I can actually do something with it, and if it doesn't, I don't get too embarrassed in front of my professional friends. Woodwinds are reed instruments. The organ pipe, the flute, the recorder are what are called edge reed instruments. The clarinet, the oboe, and the bassoon are cane reed instruments, either single reed, as in the clarinet, or double reed, as in the oboe. And that's why I asked to have one of each, because I wanted you to hear both of those instruments. One of the best books I read on woodwinds is by a man named Anthony Baines, called Woodwind Instruments and Their History. And it's hard. It took me a while to understand it, but I copied the following paragraph from it. Flutists and brass players, with all their worries, at least have the advantage over reed instruments in that their sounds are generated with the help of the solid, unchangeable material of the instruments. Oboists, clarinetists, and bassoonists are entirely dependent upon a short-lived vegetable matter, the reed, of merciless capriciousness, with which, however, when it behaves, are wrought the most tender and expressive sounds in all wind music. And I think that's really true. I find it absolutely amazing that the reed can be controlled that well. Now, I just have liked this thing, so I've sort of got it up. We're talking about waves and vibrations, so I leave that up. But here, I have a picture of the woodwind family, and so we can see two peculiar woodwinds, the recorder and the saxophone. But there's the flute and its younger version, or smaller version, the piccolo. The oboe and called the bass oboe, I would call it the cor anglais, or the English horn. The clarinet, the bass clarinet, the bassoon, and the contrabassoon. So now, but what I want to start with is an edge instrument, and I want to start with organ pipes. And the most common, because we've talked about tubes and pipes a bit on Monday, and I want to come back to that. And the most common organ pipe is a flue pipe. Because it's rather like a chimney flue. And so here we see a typical organ pipe open, and you blow air in here. There are also sometimes organ pipes that are closed at the top. There are organ pipes that have a little reed in there, but I will ignore all those because I don't really, all I want to do is talk in general about waves and these things. Now, air is blown in at the bottom, and I get a very confusing set of pressure waves that go up here. And of course, because this is open to the atmosphere, and therefore at zero pressure relative to atmosphere, they reflect. This is like a string tied at the top, as we've seen, like a string tied. And so I get a reflection. And eventually, after a while, as I did with the spring back on Monday, eventually I get a standing wave going in here. So I have stuff coming up and stuff coming back, and eventually it settles out and that into a standing wave. That's a process called, in engineering and science, called feedback. I want to, no, wrong thing. I showed you this on Monday. It's a very complicated thing, but let's only consider just this red curve in a parallel pipe. And if I call, again, atmospheric pressure, I call that 0, because I can always subtract it, then the pressure is greater or smaller inside the tube, and I get a reflection at both ends, or a node. And so I can have my fundamental, I can have this wave will work, and 3. Whereas if I have a closed pipe, well, a pipe closed at the end, I have twice the way. I have only this part, I have only a quarter, and so I have twice the wavelength or half the frequency. And I've actually managed, I think, to do that with my little plastic device here. I will try, see, now it probably won't work, but let's see. If I go, if I close it, at the end, it goes down by an octave, as this thing says it is. It says it should. Amazing, but it actually works. Now, in an open pipe, then, I can have the fundamental, I can have twice that, 3 times that, 4 times that. I can have every one of the harmonic series. Whereas in a closed pipe, I miss all of the even-numbered harmonics. And so, although, as I said, with the brass instruments, it looks like when you put your mouth on one end, that would be a closed pipe. People have played enough with the mouthpiece of a brass instrument to make that not true. And you get all of the harmonics and a much richer sound out of the instrument. Now, with a pipe organ, every single instrument needs, every single note needs its own needs its own pipe, and so these are massive instruments. Back in the 4th century, the Catholic Church, or the only church, had a council in Turkey, in what is now Turkey, which is then Asia Minor Greece, the town of Laodicea, where they banned singing in church, which took place before that. And they wrote the following, which I have carefully translated from the Greek. I actually found it on the web in English. Besides the appointed singers who mount the ambo is the Greek word for a lectern, and sing from the book, others shall not sing in the church. And that was it. And so there was no more singing in the church. That led eventually to professional singers or priests who were singing and using the Pythagorean system that I mentioned, where all tones are ratios of 2, 3, and 4. That led to the development of Gregorian chant. But in the 9th century, they reversed part of that, and they allowed instrumental music to be played. And at the same time, and with the beginning of serfdom, there were huge cathedrals that started to be built, and these were meant and did, in fact, create awe in the congregation. And the music of the organ was also used to create awe. So that, for example, in Winchester, England, there was from a 10th century cathedral, there was an organ pipe, or an organ built that had 400 pipes. And you had to get the air moving. There was no electricity, so the air was made by that way. It took 70 men, very strong men, to pump the air for all of those 400 pipes. However, that led to some fairly amazing music. Now, if you go to YouTube and you get music things, there's always now these days an advert in front. So I convert the YouTube file to an MP3 file because my son taught me how to do that. But often there is a little break before the music starts, so they skip the advert. But we should be able to hear this, I hope. Doja, please. It's there. That, of course, is Mr. Bach. That's his great toccata and fugue in D minor. And so it makes a lot of sound. But as I said, it takes one pipe per note, and so it fills a gigantic room. If I want to get many notes from one pipe, I have to introduce finger holes. And that's complex. Here I have a picture of a pipe, and it's of a given diameter, and I have 3 different size holes put in it. And here is what the fundamental would look like in pressure wave if there were no hole. But this hole is big, and so what it does is, in effect, shorten the pipe. And so the real fundamental wave is just shorter, and so the wavelength is shorter, so the frequency is bigger, and so it's a higher note. But what happens if I have a smaller hole is that I change the actual shape of the wave, and that changes this wave is now more complicated. And remember, if you will, Mr. Fourier's analysis that any repetitive signal can be made up of a series of harmonic sine waves. And so this has got lots of harmonics in it as well. And you can see an even smaller hole makes just the tiniest of differences. But a modest size hole modifies the shape of the wave quite a bit. With a recorder, instrument with which I tortured my parents at 6 years old, there is a register hole, and it plays an octave, and so it has 1, 2, 3, 4, 5, 6, 7 holes to cover the full octave scale. Okay. I won't do that. Embarrassed. However, you can, by stopping holes, you can change the note. And so there are the finger positions for a flute, starting in C here, and you've got all the 12 notes. But one of the things about this, as you would know if you ever struggled with one of these things, is if you blow too hard, it goes up an octave. Okay, that is, you get the first harmonic rather than the fundamental frequency, and we'll see that that's important. The earliest wind instrument we have is an ancestor of the flute. And this is a relative of the flute. It's called, for example, Blockflöte in German, so it's clearly related to the flute. And a cave in Slovenia has an animal bone, a hollow animal bone with holes in it that is dated something like 40,000 years ago, so it's probably the remnants of a Neanderthal society. There certainly are animal bones with multiple finger holes that have been discovered in China that are dated to at least 7,000 before the Common Era, so they're quite ancient. The recorder was a dominant instrument for about 400 years, but roughly about 1700, all sorts of other instruments like the transverse flute, the oboe, and the clarinet were being invented about that time. And the Baroque flute had great influence in the 18th century. And I have a picture of Baroque flutes. Now, let's look at a modern flute. In a modern flute, there's where you blow the air. And this raised bump, this is a piccolo, this raised bump is called a mortis. But if I go back to the Baroque flutes, there's the place where you blow, and there is no mortis. And if you could see, I can barely see from up here, 1, 2, 3, 4, 5, 6 holes, and a 7th hole down here that's operated by that little lever at the bottom. However, this flute, this Baroque flute, was used by many great composers, in particular by the greatest composer, perhaps, Mr. Mozart. And I can't resist playing you a wee bit. That's not a flute yet. That wonderful music is Mozart Flute and Harp Concerto, of course. Lovely, lovely piece. Apparently, the Baroque flute, which is what one used originally to play that in Mozart's time, and this concerto and his flute concerti were made for that instrument. They were apparently quite difficult to play. Now, the story goes that in 1831, a German instrument maker named Theobald Böhm heard a flute play with somewhat larger holes, and it was louder, and that gave him an idea. And so he introduced the modern flute in 1847, this instrument, and he invented the system of keys that cover the holes rather than putting one's finger on individual holes. And there's this piece called the mortise in the front. Now, just again, I don't know if anyone here plays the flute or if they know whether gold flutes play better than silver flutes. I've noticed that a very famous flutist, James Galway, puts a diamond on the end of his flute. I don't think that affects the tone, but it looks very nice, and maybe it even helps the South African economy, God help us all. Reed instruments are a later development than flutes or pipes, and one of the oldest is called the shawm. And this was invented in Arab cultures in the Middle East, probably around 800 in the Common Era. And it is a double reed instrument. And it was brought back by the Crusaders to Europe and became actually quite popular. It was in France given the name of a loud wood, which in French is haute bois, still the name for the oboe in French. There's another instrument called the courtal, and this instrument was much later and only possible because of great improvements in woodworking, because there are really two tubes here. This instrument plays a note which has an air column twice as long as the instrument. I have, I think, a picture of the bottom of this, where you can see this rather complicated system so that the tube is actually twice the length of this. And this led, of course, eventually to the bassoon. It appears that double reed instruments may be older in some ways than single reed instruments, which I find an interesting historical fact, if true. These are instruments called the crumhorn. I haven't been able to find out why there's a bend in it, but there is. And this instrument has the double reed on the inside, so you don't have to worry about an embouchure, which is a problem in playing all instruments. It was played primarily by professional musicians, but apparently Henry VIII was a very fine crumhorn player. That is, when he had time from not marrying and divorcing and executing various women. I don't know if it's true in South Africa, but in England, all students learn about Henry VIII and his 6 wives as divorced, beheaded, died, divorced, beheaded, survived, as what happened to those 6 poor women, except for the last one. Now, the modern oboe, which was originally invented around 1700, was finished in design by about 1850. It has a length of about 60 centimeters, and its fundamental tone is B flat 3, the B flat just below middle C. And it is made, I am told, from wood like the grenadilla tree, which is not uncommon here. The bassoon plays 2 octaves lower. It's 10 to B flat 1. And therefore, since it's 2 octaves lower, it ought to be 4 times longer because you double the length for every octave. And it is, except the bassoon, like the courtal, has a bend at the bottom, and so instead of if the oboe is 60 centimeters long, then the bassoon ought to be 240 centimeters long, that long, and it's half that size. It's 1¼ meters because it has the bend at the bottom, so it's really 2 tubes. Now, I was going to ask Andrea if she would be, you know that when orchestras tune, they tune to an A. So I was going to ask her to play an A and then an A major scale, if she would. I love that sound. I think it's just the most amazing. Now, everybody knows that orchestras tune to an A, so I tried to do, in that book I mentioned to you by Mr. Baines, he talks about why the oboe. And so I'll tell you what he says. He says it's an accident, basically, that when people first started writing symphonic music for the viol back in the 17th century, and they were quiet because they had got strings, they would often have an oboe to back up the first and second violin. So they would have two oboes. Now, gut strings are hard to keep in tune, and so they wanted an instrument. They didn't want the violinists all yelling at each other about who's got the right A, so they used an instrument that made a loud sound and could be heard over the whole orchestra. They used the oboe. And I don't know if that's the truth, but that's what I read, and it sounds quite reasonable. And I've seen an orchestra somewhere in the United States, which has an artificial electronic 440A, but even there, it was the oboist who turned it on. So tradition really matters. Now, I can show you a slide. There's the oboe and the bassoon, and there is the number of slides that I could find that tried to show how a double reed is made, and the various pieces. And I am told that not only do most, but even our present oboists make their own reeds. And that sounds like one heck of a difficult task for me, at least. Now, let's talk for a minute about the clarinet. The clarinet is a descendant of this instrument, the chalumeau. I did want to show you a hornpipe. This instrument is very, very ancient. It goes way back to Egypt and to Mesopotamia, so it's really quite old. I guess it is called a hornpipe because of the horn, but I don't know. What I was unable to find out, although I can guess, is why there is a dance for sailors called the hornpipe. And I can only imagine that maybe it's because this is a fairly simple instrument and some sailor would take it on board, and it must be very boring to spend 4 or 5 years sailing around in the world in a sailing ship, and so being able to dance or do some kind of entertainment perhaps gave the name to the dance of that instrument. Now, here I have a modern clarinet, and maybe we can hold up the present clarinet so you can see what it looks like. Notice that the clarinet and the oboe have a bell on the end. Okay, and again, without the bell, the sound won't come out. And we're going to talk about that finally, I hope, today. So I'd like to ask Ms. Dutoit if she would play also an A major scale for us on the clarinet. Can you overblow, please? Thank you. Notice if I overblow on a, I go up an octave. She did not go up an octave. I have an instrument which is conical, as is our most woodwinds, but the clarinet is a cylindrical instrument, and that makes a real problem. It does not overblow in the octave. You do not get the first harmonic, you get the second harmonic, you get an octave and a fifth. And that's called a 12th in music. And so it overblows in the 12th. And what that means for building a simple clarinet is that you need more holes to go up an octave. And so as we shall see, that makes a fair difference. Clarinets, of course, are a single reed instrument as opposed to a double reed instrument, and the reed is attached by a ligature as such. And there are two different kinds of reeds. There's a regular cut and a French cut. I'm told that you have a French cut. Is that right? And so here we can see how things are made. I was also found out in Mr. Bain's book that very early clarinets sometimes had this piece upside down so that the reed lay against the top of the lips rather than at the bottom. Now, a French professor born on the island of Corfu with the wonderful name of Hyacinthe Closet. And I think anybody who dares to name a son Hyacinth is a very, very brave person. And I'm very fond of the name. He invented the modern system of keys for the clarinet and use in the clarinet, and based it on the system that Mr. Theobald Böhm used. And so sometimes apparently the key structure is called the Böhm system rather than the Closet system. But he used originally a series metal covers and fish bladders underneath to try to seal them. Today, of course, I think they're largely cork. But there are lots of interesting touches have been added, such as chamfering the holes so that they're bigger on the bottom than on the outside. The problem of overblowing in the 12th meant that originally clarinetists would come to an orchestra with 3 different instruments, an A, a B, an A, a B flat, and a C clarinet, so that they could cover all of the scale. But apparently in the early days in music of Scarlatti and Handel, there were missing notes that just could not be played. There's also a story, and I find these stories in books, but I have no idea whether they're true or not. When Mozart wrote his clarinet music, there was an instrument that could play all of the notes, but 2 of them were hard to reach. And so the clarinetist complained, and the story that I read said Mozart, and who knows whether this is true after 250 years, but Mozart said, I wrote them, you play them, it's your job. It sounds not an unreasonable thing to do, but by the middle of the 18th century, certainly by the time of Johannes Brahms' wonderful clarinet music, we had the standard clarinet that we know today. And yet still, clarinetists come to the orchestra with a B flat and an A instrument. Now, I talked a bit before about holes. Let me go back to that a little bit. Here we see a reed flapping open. Here are just tubes with different size holes. And here again is that picture of the system with different sized holes and what effect it has on the wave shape. Good. Now, one of the amazing things about science. Oh, before I do that, I had one more piece I wanted to play for you that I could not resist.